Thanks a lot, Matt. And not all Canadians are polite, by the way. I've met some real doozies. So we're going to talk today about Hadoop forensics. And you can't talk about forensics without first talking about breaches. And when you look at breaches, the source of breaches or the cause is good old-fashioned hacking, okay, more often than not. And when people break into systems and they steal data, more often than not, that data is actually stored within a database. Okay, so I've been preaching the importance of database forensics now for just over 9 years, which makes me feel really, really old. But at the same time, the industry is changing. It's evolving. It's not just about databases. It's about data. A lot of organizations are taking data out of databases and they're storing it in big data technology. Okay? When you look at the big data technology who's been deployed more than any other technology in the world, that's Apache Hadoop. So when we're called in to do investigations, a lot of times the trail leads to the databases. We can investigate based on the stuff that's been published, so my own research, the books, the tools. We can investigate, we can determine what the hacker did within the database. But when you look at modern databases, they have connectors to Apache Hadoop. So the trail doesn't stop at the database. It keeps going now to big data technologies, and forensics hasn't made that leap yet to Apache Hadoop and other big data technologies. So the goal I have today for this talk is we're going to take a look at, and we're going to get our feet wet in Apache Hadoop forensics. And a pet peeve I have are presentations that are too high level. So you get the presentation, it seems cool, but you get down to actually do it, and you're not sure exactly what to do and when and why. So in 25 minutes-ish, we're going to step through the actual commands that you can run to conduct a Hadoop forensic investigation, why you should run them as well. So you're going to leave today, you're going to go back to your jobs, you're going to get a call regarding Hadoop investigation. You can just grab this presentation, nothing else, and actually run through an investigation. So we're going to do all that in 25 minutes, or your money back. Okay. So before we jump into things, I'll tell you a bit about myself. So I'm Kevy Fowler, and just a show of hands, how many of you think Kevy is my real name? It is my real name. I got a tougher question for you, though. What's the background or the nationality of Kevy? It's not a very common name. You can put Kevy in Google, and I pop up. There's no one else. So what's the background of Kevy? Any brave souls? Canadian? That's correct, but the background of the name is actually Irish. So as you can probably guess from looking at me, I don't have a ton of Irish in my family tree. I just have an Irish name, but please do call me Kevin, or Kevy. I've met a bunch of people today who've changed it to Kevin automatically, so just call me Kevy. I'm the National Cyber Response Leader for KPMG, so that means I wear two hats, and I'm based out in Canada. The first hat is helping organizations identify what information is important to them, ensure they have the right safeguards in place to actually protect that information. So we deliver services like red teaming, blue teaming, incident response, forensics, governance reviews, etc. And then when a suspected intrusion actually happens, the second hat is reactive. So I'll lead teams that will go in and confirm or deny if something actually happened within an environment. If something did happen, we investigate and precisely scope what happened. And the better job you can do scoping, the lesser the impact is to the organization. So I get both the proactive as well as the reactive sides of cybersecurity. I'm author of Data Breach Preparation and Response, which was just published last week, so I'm sure a few of you here have already bought a copy. Everyone's looking the other way. No one's maintaining eye contact. I'm going to assure that hasn't happened. I'm also author of SQL Server Forensic Analysis, and I'm contributing author, meaning I've written chapters for a bunch of other security and forensic books at the bottom of the slide. Okay. I'm also a SANS lethal forensicator, and I speak a lot at conferences. So enough about me, let's jump into Apache Hadoop forensics. So when you look at Apache Hadoop, has anyone here, I'll actually ask the question, has anyone here actually worked on an investigation involving Apache Hadoop? No one yet? And I hope everyone's going to be honest. Does anyone here not have the faintest idea what Apache Hadoop is? Even the AV guys know. They're like, no, I know what Apache Hadoop is. So Hadoop is basically just a framework to store information and to analyze information. So you can go out there and you can download Apache Hadoop. You're going to install it, and what it is, basically, it's just a file system. So it's just Hadoop distributed file system. But it's modular. you can add a lot of components on top of Apache Hadoop. So you can add database servers, and there's a variety of different database platforms you can add on there, relational databases, SQL, NoSQL. You can add advanced search functionality. So you can add a bunch of components onto Apache Hadoop. In the 25 minutes we have today, we're not going to cover how to do an investigation across all of these components. We are going to focus on the core of Apache Hadoop, which is just HDFS. Okay, so that's just the file system. And we're going to look at Hadoop version 5, and Cloudera 5.7 was what was used for the research in this presentation. But other versions of Hadoop, the same principles, the same commands, et cetera, work. Anything over really Hadoop version 1. Okay. So what does Apache Hadoop actually look like? This is a scaled-down representation of what an actual Apache Hadoop implementation looks like. Okay. There are some other components that aren't relevant based on what we're going to talk about today, so I've actually omitted them from the slide. But I'm going to start on the right-hand side for you viewing out there in the audience and work my way to the left-hand side of the screen. So every Apache Hadoop implementation has a lot of data nodes. Okay? And these data nodes do nothing more than just store information and follow orders. So that's where the actual data is stored. So you're doing an investigation, you want to suck information out of Apache Hadoop, you're going to grab that information from your data nodes. Then you have a job tracker. And what the job tracker is, it focuses on just mapping and reducing information. So if you look at Apache Hadoop, their claim to fame is instead of moving data to processing, it moves processing to data. So you folks here in the US are going to be going through an election fairly soon. I'm going to reserve comments about some of your candidates. But for an example, if I wanted to store a file in Apache Hadoop that had a listing of all the registered voters. Number one, Apache Hadoop works on replication, so I add one file, it automatically creates a bunch of other replicas. It takes all those replicas and it spreads them across all the data nodes. Okay? And then if I were to send a query to Apache Hadoop saying, give me all registered voters who have a first name that starts with A, B, or C. What the job tracker is going to do, it's going to talk to the first data node and say, you give me all registered voters who has a first name that starts with A. It'll go to the other data node and say the same thing, but with B. In the third data node, give me all registered voters with a first name of C. So it maps the work out to a bunch of data nodes. The data nodes do the work, and then they send the results back to the job tracker, and it reduces all of those results into one and sends that back to the person requesting it. So job tracker just works on mapping and reducing work. Then we have the name node. And the name node is where all the metadata is. When you look at Apache Hadoop implementations, it's not uncommon to find multi-petabyte installations. When it comes down to forensics, you can't image everything. You can't image several petabytes. Okay? So you really want to focus on that metadata, and that's the server that all that metadata is stored on, which is your name node server. We'll get into more details on that in a little bit. Then you have your interfaces. So anyone who wants to interact with Apache Hadoop, it has to come in through an interface. You can do so via MapReduce jobs. That's equivalent to query in a traditional database. Okay. You have a command line, so you can actually get in there via a command prompt. You can get in there via the web as well. So every node within Apache Hadoop actually has an integrated web server. I won't talk about security in this presentation, but they all have web servers within them. You can actually navigate from system to system, and they have an API. Okay, so all that information is within Apache Hadoop, and that's how you actually get information in and out of Hadoop. And then most Hadoop clusters, for authentication, they connect back to an LDAP server, and they normally have management systems that allow you to manage hundreds and hundreds of nodes. The limitation within Apache Hadoop for how many nodes you can actually have is 4,000. And again, a lot of these are multi-petabyte installations. So that's typically what an Apache Hadoop installation looks like. So from an investigation standpoint, that's great. You understand Apache Hadoop, why it's important to manage investigations leading to Hadoop. But what can you actually get out of Hadoop? And there's lots of different artifacts, but we're going to focus on a handful today. We're going to focus on cluster properties, how to figure out what you're actually dealing with when you're called in for an investigation. Logging, how the cluster is actually set up, because that will impact your investigation. The metadata we talked about, we're not going to image petabytes and petabytes. We're going to take petabytes of information. We're going to just look at the metadata, and focus on just the gigabytes of information that are relevant to the investigation we're investigating. And metadata is going to be how you do that. And Hadoop is not a database, but it does have a transaction log. So we're going to take a look at the transaction log and see what information we can get out of that, and also how to retrieve files out of Apache Hadoop. Again, all of that in 25 minutes. Okay. So jump into cluster properties. So if you get a phone call saying there's an investigation, it's leading to Apache Hadoop, the first question you're going to ask yourself is, what am I dealing with, and how long am I going to be stuck here imaging this thing? Okay? And to answer those questions, you're going to need to get information about the cluster. And that comes in the form of cluster properties. So some of the properties you're going to want to know are how many nodes are in this Apache Hadoop installation, and how big is it? Are we dealing in gigabytes, terabytes, or petabytes? There's a few different ways you can get cluster properties within Apache Hadoop. You can do it via the web, so via the different web servers on the different nodes within the cluster, or you can do that via command prompt. And just focusing on the web for a second, you just type in the address that you're looking to connect to, so the IP address and the port, and it will actually dump information about the actual the nodes within that Apache Hadoop installation. So I've highlighted a few areas on the slide here. We have live nodes. How many nodes does this cluster actually comprise of? And in the example I have, it's actually running in a VM, so it's one live node. But the real juicy information comes down to the name node storage. And that's image and edits. That gives you the actual path to all of that metadata that you need to actually reduce an investigation, theoretically from petabytes to the relevant gigabytes of information that you need. So you want to make sure you get that path and you write that down so you know where to get access to this information in a little bit. And you can get the same type of information via command line, via HDFS DFS admin, which is an integrated Hadoop utility that allows you to dump similar information out via command prompt. Okay. So when it comes down to logging, there's tons of logs within Hadoop. We're not going to cover the tons of logs. I'm going to generalize here just in the interest of time. So if you look at the core site.xml file, it contains general properties about the entire cluster. Most relevant within that file comes down to the trash management processes. So when you delete files from Hadoop, can you still recover them? And you can recover them from an area within Hadoop known as trash. And even when it's moved from trash, it's moved to another location, you can still recover it. And even when it's deleted from there, you can still recover it based on the next location. But all of that configuration is within that file, so that will help you understand what you're dealing with. HDFS site.xml, that contains information just about the Hadoop file system. So that will give you the path, the directories, how it's configured, how many replicas it's storing, et cetera. So that'll provide you information about that file system. Then it comes down to MapReduce, the site.xml file. That will tell you how MapReduce is actually set up. And in that file, actually lists a temporary directory that it uses for Scratch. So when queries are executed within Hadoop, it sometimes stores temporary results within a folder. You can actually go to that folder and get an idea of what past commands were that were executed based on that Scratch location. And last but not least are log4j properties, and that contains information regarding the configuration of a lot of the daemons running on the systems and the nodes within Hadoop. Okay? So those are the key configuration files that tell you how the cluster is being configured, and that's going to tie in when we jump to analysis. So when looking at Hadoop, we talked about the focus is just HDFS, which is a file system. And when you look at a file system, Hadoop stores all information in the file system, so all files, all folders, and the structure of that, all within what's known as an FS image file. Okay? And that FS image file, again, stores files, folders, et cetera, but it's not complete. Hadoop contains information about the file system, but it also contains a transaction log. By default, the transaction log stores 1 million operations within it. So to get the accurate picture of the layout of the cluster, you have to look at both the FS image as well as the transaction log. From an investigation standpoint, it's not fun to look at those two files and try and manually correlate what happens. So I might look at a folder within my FS image named Kevy, but there was a transaction executed last week renaming that folder from Kevy to Fowler. I would have to manually map that transaction to my image to figure out what the file system actually looks like. So before you dump any information out of FS image, I recommend you run a checkpoint. And that checkpoint takes that transaction log And that FS image, it brings it together, and it comes up with an up-to-date FS image file. So you want to checkpoint first before you dump information. When it does that checkpoint process, the current FS image gets moved to archive and a new one is created. So if you look at the screen capture below, that's just using File Manager, but that's looking at the actual file system of the Linux file system with a name node installed on it. And you see there's several FS image files, and you notice an FS image file with a number at the end. That number at the end represents the last transaction to modify that file system image. The file underneath it with a .md5, that of course is the MD5 file hash, and Hadoop uses that for integrity matching. Okay. So you're going to want to make sure you run the checkpoint before extracting information from your FS image. And that begs the question, how do you actually get information out of the FS image? There's an integrated utility known as Offline Image Viewer, and that allows you to actually extract information. You can put a delimiter in there as well, so you can export that to a file, and you can incorporate that into whatever timeline application you're using to factor that into the broader investigation. What's happening in the network, what's happening in the operating system, and now what's happening within Apache Hadoop. The timestamps within Apache Hadoop, when you look at last access times, those are accurate up to 1 hour, which is a little odd. If you think about modern operating systems such as Windows, NTFS, those are instantaneous, right? Wrong. Trick question. Does anyone know what the delay is for Windows, NTFS, last access time by default? 1 hour. You got it. You can even disable it altogether. A lot of people look at the last access times, think that's guaranteed to be accurate. It's accurate up to 1 hour, just like Apache Hadoop. You can even turn off or disable the NTFS last access times. You can do exactly the same thing within Apache Hadoop. So HDFS is very similar to NTFS regarding how it actually operates. But that's how to extract information regarding the actual files and the folders. So if you're doing timeline analysis, you want to know what files are accessed or modified within a certain time frame, you want to dump your FS image. After you've run that checkpoint, you can figure out who's been doing what within your Apache Hadoop cluster. Second half of the picture, which we talked about, is a transaction log. That's actually called the edit log within Apache Hadoop. And similar to the FS image, whenever you run a checkpoint, the current edit log, which is named edits in progress, gets moved to the archive. And you see there's 3 archives above that file in the screen capture. If you look at the top edits file, you'll notice there's 2 numbers. There'll be edits underscore one number dash another number. Those numbers represent the first transaction that actually modified data on disk within Hadoop, and that last number is the last transaction that modified information. And the interesting thing is it actually tells you the range of transactions within the file. So you can go back to a past FS image or a past edit log, we'll say 1 week, 2 weeks, or 3 weeks ago, and actually get an exact copy of the way the file system looked like and what the transaction log looked like in the past without restoring from backup. So that's actually pretty helpful from an investigation standpoint. So when you look at the actual information that's stored in an edit log, again, Hadoop's edit log is very similar to a transaction log, so it stores operations. And there's lots of different operations. I'm not going to cover all the operations today. Okay? I will cover a few, and not even all the ones that are highlighted. But I'll cover op-add. Anytime a file is added to the Hadoop file system, it's logged in that edit log with an op-add operation. Op-rename old is anytime you rename or move a file. It'll be logged as op-rename old. Whenever you delete a file or make a new directory, it's logged in op-delete or op-make directory. Skipping over a few op times or any time you modify the timestamps of a file or a folder, there'll be an op-time operation. And the op-end log segment and op-startup log segment are your default. Any edit log will have those to mark the start and the end of it. Those are just a few operations within the transaction log. So that's well and good. You're called into an investigation. You're looking at an edit log that has 1 million entries. How do you figure out a summary of what's actually happened within it? And to do that, you can actually use the OEV, not to be confused with offline image viewer. This is offline edit viewer. So you can actually use this utility with the processor argument, and it will dump a summary of all the transactions. How many files were added, deleted, modified, renamed, all of that good stuff is in there. So I recommend if you're on the cluster, you want to type that command and make sure you have that summary, right? You're going to change your standard out, make sure you have that summary and you understand the type of information within 1 million of those transactions in your transaction log. Okay? And despite the name offline, you actually run it against online files, which is kind of confusing, but that's the way Hadoop does its thing. Okay? So after you understand the summary of what's in there, you want to actually take a look at the transactions in that transaction log. And just changing your processor, so eliminating the processor argument, you can actually dump information in plain text out of your transaction log. And what type of format does that look like? XML, you got it. So it dumps information out in XML format. And when you look at Apache Hadoop, there are lots of operations. You add a file to Hadoop, there's a lot of intercluster communication. So you add one file, there might be 10 operations that are added to that edit log. The very last operation is an op close, and that's cumulative and contains all of the information in all of the other operations. So whenever you're looking at any transaction, you want to look specifically at the op close, and that will be cumulative, and that will give you all your information. If you're looking at some of the earlier operations within that transaction, you're only going to get partial information, so make sure you're looking at the op close, and that's highlighted there under operation. Then you have the actual unique transaction ID associated with Hadoop. Then you have the file that was actually created. This is an example of someone creating a file within Hadoop, and you have your modify and your access times. And what format do those times seem to be within? What do you guys think, based on my Linux and forensics people? Epoch, you got it, epoch. An epoch can be either seconds or milliseconds, and that's milliseconds. So that's the number of milliseconds since January 1st, 1970. And it gives you information about blocks and the file permissions as well. You can actually go through and map out what user did what, who added a file, who deleted a file, who renamed a file, what the internal Hadoop system was doing. So it's very, very good from a forensic and security standpoint to backdate what happened. And again, you get 1 million of these operations within that edit log. It's not by size by default. It's by the number of operations it stores. And you can get 1 million out of this edit log. Okay. So you've done the investigation. You understand what the file system looks like. You understand the type of operations that were there. And you've likely identified some files that you care about. Maybe a hacker broke in. I can't use hacker. I'm used to speaking to board members and audit committees, and I can't use cyber attacker or the other terms, so I use hacker. So I'm not at those type of conferences now. So a cyber criminal breaks in and they store a file. It might be malware or something else within Apache Hadoop. So you got a file of interest that you want to actually check out. So how do you actually get the information out of Hadoop? There's utility within Hadoop, HDFS fscheck, that will allow you to get information about a specific file or directory. And that will tell you where the file is located. Remember, every time you add a file, Hadoop makes a bunch of replicas of that file. So you can have hundreds of data nodes, but the file is stored on maybe 3 of them. So you want to make sure you can get the IDs of the actual nodes that contain the files and the block IDs. You can get all that with this command, and that will dump the information via command prompt. Once you get that, you navigate to the actual server, and you're just in the Linux operating system, assuming you've installed Hadoop on Linux, and you map to the actual location that contains the block, and you can get the block. You can just simply use whatever imaging tool you're used to using, DD, DCFLD, whatever, and just image that block. And that allows you to extract the file from Hadoop while preserving the timestamps. Hadoop has some native utilities that allow you to take files out of HDFS and dump it out in the local operating system, but it clobbers your timestamps. So this way we allow you to do it while preserving your actual timestamps. And despite Hadoop being installed on top of a server, all the files are just blocks and just data, text files that are stored in the local file system. So you can go through Hadoop to extract data, or you can go in through the local file system and steal it. Hadoop won't even know you were there. Okay, so this is the way coming in via the back door. So when you look at trash, when files are deleted from Hadoop, they're not deleted forever, of course. When you delete a file, Hadoop just moves it from the original location to a trash directory. It stays in that trash directory for a little bit of time. It's then marked for deletion, and it's moved to a new structure, which is transaction ID, month, date, and it's stored there until a process comes by and actually deletes that file. Okay? So during that process, after someone deletes a file, you can still go to the trash directory and retrieve it. You can go to the other location that I mentioned and retrieve it there while it's scheduled for deletion. But even after it's scheduled for deletion, and we'll say it gets deleted, do you think it's gone forever? 50% chance. Who wants to guess? Who's a brave soul? No, there you go. No, it's not. Because it's just a file in the local file system. When you have a file in Linux or a file in Windows that gets deleted, you still recover it. It's no different within Apache Hadoop. So there's multiple levels you can actually recover a file from when coming through Apache Hadoop. And keep in mind, there are some caveats here. So deletions done via an API don't go to trash. Okay? When a user might be on command line, you can actually delete a file and specify not to go to trash. So there are a few ways you can try and get around the trash process, which isn't enabled by default, but Hadoop or Apache recommends you enable it. Okay? And even if it's not, and it's deleted from the local file system, again, you can still recover it using your standard data recovery tools. And the last slide I want to talk about today are threats to look out for. So we've talked about Apache Hadoop and it being a file system. I told you earlier today we're going to focus on just the file system. I sort of lied because I got one slide talking about some of the add-on applications. Okay? There's a lot of databases. I think there's 3 or 4 different databases you can add on to Apache Hadoop. And a lot of organizations focus on the traditional development, whether it's .NET or Java or C or whatever language they're developing in. They have software development life cycles to help ensure they got secure code. Okay? And the SDLC is working great over here. But as soon as you talk big data, organizations spin up a big data technology or platform. They bring in sometimes some consultants, sometimes it's in-house people. They develop things and they do their own thing. For whatever reason, the SDLC doesn't map to big data implementations. So a lot of the vulnerabilities that you had with traditional development languages back in the early 2000s, late 2000s, are still present within Apache Hadoop. One of the databases you can add on to Hadoop is called Hive. You interact with it via HQL or HiveQL. And guess what? HiveQL is still susceptible to SQL injection. So I'm not going to get into first-order SQL injection attacks or second-order SQL injection attacks, but simple, dynamic, blind, stack queries, all that good stuff you can still do within the Hive via HQL. So for those guys in the audience here, guys and gals who are red teams, when you look at your attack paths or your attack trees, you can actually come into an application via SQL injection, so web server to database. Modern databases have connectors to Apache Hadoop, SQL Server 2012 and higher. Leverage an HQL vulnerability to extract information out of Hadoop, return it to your database, and then return it to your web browser with you halfway across the ocean somewhere. So when you're looking at attack paths, don't count out Hadoop. It's connected to more things than you might think it is. From a forensic standpoint, make sure your standard operating procedures cover Apache Hadoop as well. So we covered Apache Hadoop, some of the commands to run to actually figure out what you're dealing with, how to get information about the file system, how to look at the transaction log, and how to pull it together, and also a new threat with HiveQL. And we talked about the Hive, but you have Impala, you have Spark, there's lots of other database type products within Apache Hadoop. I haven't done the research there, but if I was a betting man, I'd go all in to say they have the same weaknesses regarding HQL injection. So based on what we covered today, are there any questions that you have on Apache Hadoop, my Irish heritage, whatever it is? Yes. With Hadoop, you can install that on Linux or you can install it on Windows. So you're going to have a standard Linux server. It's going to be your ext2.3. You're going to install that within Windows. That's going to be NTFS. That's going to be standard. You install Hadoop on top of it, but it still stores files in that local file system. So it's no different from a standard Linux server, no different from a standard Windows server. So it's what we all know about. The same tools you have, the same techniques can all be used to steal the blocks right out of Apache Hadoop, and it won't even know you were there.
For one more question? Anyone?
One more question?
We'll only keep you off this easy. All right. That's it. Thank you very much.
Thank you. Everyone enjoy the rest of your conference.